Welcome to Lecture 8. This is about dependent random variables and where they can be used. We'll start by looking at independence tests and first of all, what dependent and independent random variables are, and also how we can identify whether we have dependence. The second block is to look at sequence models, how they're designed, and how you can then use them to, for instance, design recurrent neural networks. We'll look at specific forms such as RNNs and autoregressive forms. Transformers will happen later in this class. And last but not least, we'll cover graphs. And well, it's not clear whether we will have time to cover this in the actual lecture, but I'm recording it anyway. Okay, so let's dive right in. And yeah, people do a lot of testing, so we can also test for HSIC, namely whether random variables are independent or not. Okay. Now let's have a quick look at dependent or independent random variables. So let's say I start out with those variables up here. And this is, they're just observations. 1, 2, 3, 4, 5, 6, 7, 8. Oh, 7 actually. Then I could, so let's say these are our xi's. I'm observing some yi's. And the question is now whether those yi's down here are dependent or independent on x. And if you first squint at it, you might struggle to see whether it's one or the other because, these are now just cartoon cats and dogs. And, does Garfield really look very much like this tiger cat? Well, maybe not really. But once you see what the trick is, namely, well, they're both cats. So this is cat, cat, dog, cat, dog, dog, cat. You can see that the x's and the y's are very clearly dependent. As a matter of fact, you could actually think about the following model where we have, let's say some type, and then we pick a photo and we pick, in this case, a cartoon. And well, it's very clear that in this case, well, photo and cartoon are dependent on each other, well, because they have a common ancestor, namely the type. Now you could ask the question, well, what about those below? Because, well, this is clearly, not so nicely paired, right? There's a cat, there's a dog, or maybe, here's a dog and there's a cat. And again, if you look at it a little bit more closely, you can see that it's more or less the same thing as what we had before. Let's just call them maybe yi primes. And well, if we label it, it becomes painfully obvious, right? That's dog, dog, cat, dog, cat, cat, dog. So it's actually the inverse of what we had above, right? So again, you could still model this in the same dependency model. The only thing is that, either the cat or the dog now gets inverted. So these are examples where the random variables are very strongly dependent on each other. And if you knew whether it's, a cat or a dog, then you would be able to synthesize the corresponding observations very easily. And if I have a classifier, well, then I could, for instance, classify the top row and then have it generate the bottom row or vice versa. The really important part is, as you can see, that p of x and y is not factorizing in p of x and p of y. By the way, in general, this is the case. Obviously, there are certain things that are reasonably independent, like whether my washing machine runs and whether my car has enough fuel in the tank. But you could easily imagine situations where both become dependent. For instance, let's say we have an earthquake. Then in the case of an earthquake, you might not have enough fuel and the electrical power grid might be down, and so in this case actually conditioned, so they would have a common cause for the malfunctions. Okay. Now, I can have a situation where random variables are independent. And by the way, just to drive home the message, it doesn't have to be perfect, right? It's okay if occasionally, for instance, rather than a cat, we see a dog, maybe we see a crocodile or whatever. But it can be, entirely imperfect. But if there is no dependency, basically if I just, toss a coin, and if it's heads, it's a cat, and if it's tails, it's a dog, then, I can correspondingly, do that, for cats and, for the top and the bottom row. In that case, truly p of x and y would factorize into p of x times p of y, right? If that's the case, this simplifies a lot of our life, but it can actually also make things a lot worse, because in that case, sometimes we can actually not do what we set out to do. So let's just actually look at what this behaves like in reality. So if I have dependent random variables, so if x and y cannot be written as p of x times p of y, then I can just by, base rule write, p of y given x, that's just conditional probabilities. I can write it as p of x and y divided by p of x. Okay, I can always do that. Now, as such, I can therefore infer, or at least get a good guess of y if I know x. I can use that for A/B testing, for cause and effect. I can use it for classifying images, like whether, this is a cat or a dog, or, well, whether Alex is looking at the camera or looking down, right? All those things I can infer. Now, if I have independence, so in other words, if p of x and y is given by the product, then reusing that same equation up here, right, I now can plug in the form for p of x and y, so it's p of x times p of y, in which case immediately p of x cancels out, and so I just have p of y. In other words, p of y given x is the same thing as p of y. And that's exactly when y is independent of x. So in statistician speak, we often write this as y being independent of x. Now, in some cases, you may actually say, well, two things are independent of each other conditioned on a third one, right? And for instance, if you recall the situation with the real cats and the cartoon cats, what we might have is the following situation where, conditioned on the type, so whether I'm going to create, a cartoon cat or dog, or whether I'm going to take a picture of a cartoon of a cat or a dog. So this might be the photo. This might be the cartoon, right? Then you will see that, once I tell it, okay, give me any cat or dog, or give me any drawing of a cat or dog, those two things now become independent of each other if I only know the type. This is what's called conditional independence. Okay, this is a very useful property, because usually conditional independence tells us that I've discovered some other variable which explains, or is a common cause for those two individual ones, or at least where, knowing this additional variable, I no longer have to worry about any specific values of one or the other, but that, third variable sufficiently separates the statistical estimation concerns between the individuals. Okay. Now, obviously, if we have such a nice and desirable property, we might want to go and test for it. a simple discriminative test is to train a classifier between, x and y pairs that are matched and unmatched pairs. So what I might do is I might, take as my original data the pairs x1, y1 up through xn, yn. And then for the other class, I might have, pairs x1 permutation of 1. So in other words, I'll get pairs like maybe x1, y3, x2, y42, and so on and so on. So there'll be just, random combinations of x and y's. And pi is just some random shuffle, so this way I use every x and every y just once. Now, if my classifier can distinguish between such data, then we have dependence, and we've established that it exists because, well, the classifier can tell us, and as a collateral benefit, the classifier will go and identify particularly strongly related, thus easy to spot pairs between x and y. Because just because x and y are dependent doesn't mean that they're always dependent or always strongly dependent. It just means that overall that property exists. Okay, so in terms of the conversation of, well, if you have a classifier, you get some nice collateral benefits. Well, if you think about it, your classifier is going to be one where, for matched pairs x and y, f of x and y is greater than 0 for dependent ones, and I might have f of x and y prime, less than 0 for independent. And as such, of course, I can go and distinguish those two. Now I can turn this around and ask, well, given an x, what kind of y would make this x and y pair look the most dependent possible? And the easiest way to do that then is to take this function f of x and y and run the argmax with regard to y. So suppose I have pairs of images and labels. Then I could try to train a classifier, binary classifier between images and their correct labels, and turn this into a multi-class classifier by just asking that function, find me the y which has the largest compatibility score between y and x. So this is not a bad idea for training a classifier. It's maybe not the very best, but what you can see is that this is a nice reduction, first of all, of an arbitrary, classification or regression or whatever problem to a binary classification problem. So this is actually a very, fertile area where you can reduce a lot of problems to classification problems. The reason why people might do that is because if I have a really effective classifier around, then through those reductions, I can turn it into a very effective estimator otherwise. So about 15 years ago, a guy called John Langford wrote a lot of papers in this area, and he released a library called VW, Walpole Wobbett, and I'm probably mispronouncing it. And for a while, this was kind of the leanest and meanest classifier you can find. It's still a pretty good tool, but, technology has advanced. Okay. Now, there are more advanced tests rather than, just training a classifier. And one way how to do better is to just ask, well, can I design something where I want to measure the, expectation in Hilbert space? So remember, we talked about spectral methods before, where we went and compared, two distributions. And what we did is we basically computed the p expectation of phi of x minus the q expectation of phi of x. And then we took the norm of that and we said, well, if p and q are the same, then this term vanishes, and if they're not the same, then this term will be large. So now what I'm going to do is I'm going to use as my p expectation term one that looks like p of x and y, as my q expectation term one that looks like p of x times p of y. So basically this is the factorizing term. I'm going to plug this in here, which is exactly what we have, right? And then, okay, well, for good measure, I'm going to square it just because it looks prettier. So what this does is I'm just going to take a joint expectation and an independent expectation, and I'm going to compare those two. Now, if my feature map or my representation factorizes nicely into an outer product between x and y, this is exactly what you might want to use. If it doesn't do that, then you might have to plug in something like just phi of x and y in here. And likewise, you get that, phi of x and y. And one of the reasons why this is more awkward is that now in order to take the empirical average over x and y, you would have to compute the sum over I and j, 1 over m squared, phi of xi, yj, right? And as such, you can then go and nicely, compare joints and not joints. But this is now an order, if you don't do anything clever, it becomes an order m squared algorithm, which is why people really, really prefer taking individual expectations here and then taking products. So if things factorize nicely, then we get this very simple expression here. This is now the function that maximizes the discrepancy of the means, and it's a very straightforward expression. It turns out that this is also the covariance operator that we get implicitly through that. So if we were to take the norm of this function here, that would be exactly this thing there. So it's fairly easy. Now, since this is a practical machine learning class, I don't quite have enough time to go into a lot of detail. Suffice it to say that the covariance operator, or this is basically, the function analysis version of a covariance matrix. So think of matrices in infinite dimensional space, and you get an operator. In any case, this covariance operator, well, that has to vanish if things are independent, right? It's just like general covariance has to vanish. Now, the covariance operator can be written as the expectation, the joint expectation of, the feature map of x minus its mean. Okay, and I've forgotten another bracket here. Okay, times the, feature map in y minus the expectation, minus its mean. And then I just take the joint expectation of this entire term. And by just Bayes' variance decomposition, you can get this expression here, which just so happens to be exactly what we saw before. So if you look at this and compare it to that, it's the same thing. The funny thing is actually that there were two criteria that were invented at the same time, and then it took a little while for us to prove that they were actually the same thing. So people had written papers on both pieces independently, and then it took us a while and to sit down a bit of linear algebra to prove that those two things that worked both fairly well were actually the one and the same thing. Okay. Now, if you want to skip all that baggage, all you need to remember is just that you need to compute the trace of HKHL, where H is just the centering operator, so this basically just takes out the mean, and then K and L are covariance matrices. And if that term here is small, you know that things are independent. If it's large, you know that they're dependent. Okay, now there's a last way how you can get it. And if you recall, this is this 1, 2, 3 punch that we've done so far quite a few times, right? So quite often we used a classifier. Then we went to spectral. And then the third step was we used information theory. And just as before, we can see that also for independence, we can use any one of those three things, or we could also combine it. So the information theoretic approach would be to look at the Kullback-Leibler divergence between the joint and the product of the marginals. And so now if we plug this in, right, so this is dp of x and y, log of p of x and y minus log of p of x times p of y. Okay, so far so good. Now I can split this up, obviously, into log p of x plus log p of y, right? That's just by the addition versus multiplication within the logarithm. Now the next thing to realize is that if I have an integral dp of x and y, and my integrand doesn't depend on y, then I can just drop this because it's a proper probability distribution. So therefore I then get minus log p of x times dp of x, so that's just the entropy in x. I get the same term in y. And then I'm left with, you know, that entire first expression there. And that one is nothing else than just the joint entropy. Well, actually the negative joint entropy. This quantity has a name, it's called the mutual information. And essentially what this says is the mutual information vanishes if x and y are independent of each other. Well, which is a nice intuitive way of looking at mutual information. Basically, if x and y are independent of each other, then knowing x tells me nothing about y, and vice versa, there is no information about y in x. Okay, now the other thing, so if you recall, the Kullback-Leibler divergence also measures the extra amount in nats. Okay, it's not bits, it's nats, so it's not binary code, but it's basically code based on E. How many nats there are extra if I use, well, the product of the marginals to encode the joint, or in this case, the joint relative to the marginals. And so what that means is basically how many extra bits or, you know, amounts of information I need to spend if I were to encode the x and y pairs independently rather than encoding them jointly. And you can clearly see that knowing if the data is independent, no bits can be saved. Here's an extreme example where a lot of bits can be saved. You would hope that a compressed file is very strongly dependent on its original content, especially if it was a lossless compression. Basically get that h and y, let's just actually look at what happens if basically, so suppose x is compress of y. So in that case I will get that h of x and h and y are the same. And you would also get that the joint entropy is the same thing as 1, because essentially I only need the original or the joint to encode it. So I get that this is also h of y. And so therefore you get that you have h of y plus h of y minus h of y. So you will get that this is basically the entropy in y. In other words, the original and its compressed version that's completely losslessly compressed is exactly the information in the original data, which makes a lot of sense.